This is Unit 4, Part 2 video. We're going to talk about exponents here. So I always start by reviewing some laws of exponents that you've seen and worked with in the past, because we all could use a reminder of those. So let's just write those down, the laws of exponents. And you're going to have similar laws when we talk about, and properties when we talk about logarithms soon. So the first would be that when you are multiplying with the same base, you add the exponents. When you are dividing with the same base, you subtract the exponents. And a power to a power, you multiply. Another good one to know, and that many of you know, is that a to the negative x is the same as 1 over a to the x. Of course, anything to the 0 power is 1. And the other one that people often need reminders with about is fractional exponents. So a to the x over y, the denominator in that fraction is the root, so you can think of it either as taking the y root of a and then raising it to the power of x, or you can think about it as a to the x, raising a to the power of x, and then taking the y root. Either way. Okay, so those are the laws of exponents. So far, when we are solving for a variable in the exponent, the strategy that we have is write both sides in terms of the same base. So if you have a single term on the left that is a base to a power, then you'll have a single term of the same base to a power. The only way those two sides are equal is if the exponents are equal. So let's do a few examples here. And then we'll more broadly talk about exponential functions. Okay, so if I said solve for x, again, we're going to do several examples here. All right, first one. And I tried to make them a little bit different and challenging, so you can just kind of see a variety of types of problems. And feel free to try this on your own first, and then you can come back to the video if you want and see how you did and see how I went about it. So 5x, my goodness, sorry, making this a little sloppy. So this is to the 5x minus 7 over 3 to the x plus 5. Okay, so the first thing that I look out here is, all right, I've got a lot of different things raised to exponents. What can I write them all in terms of? Which base? It looks like I can write all of these in terms of base 3. So let's do that to start. So 1 over 27, well, 27 is 3 to the third. So 1 over 27, I can write 3 to the negative third. Square root of 3 is just the same as 3 to the 1/2. And then 9 is 3 squared. And the denominator here is already written in terms of base 3. Okay, so let's clean things up. So over here, 3 to the negative 3 to the power of x minus 2. Well, a power to a power we multiply. So it's 3 to the negative 3x plus 6. Power to a power you multiply. So times 3 to the 1/2 x equals 3 to the 10x minus 14 divided by 3 to the x plus 5. Okay, almost there. So on the left side, I've got same base, I'm multiplying, so I'm going to add the exponents. So it's going to be negative 3x plus a half x, which is negative 2.5, or negative 5/2 x plus 6 equals, on the right side, same base, you subtract exponents. So it's going to be 3 to the 10x minus 14 minus x plus 5. Instead of doing that in my head, I wanted to show you it out in case there were problems with distributing the negative. So I've got 3 to the negative 5/2 x plus 6 equals 3. It's going to be 10x minus x, so it's going to be 9x. And then it's going to be a minus 14 minus 5, so minus 19. I can tell right now these are not pretty, probably not going to be a pretty answer. All right, now I have exactly what I want. a single base on one side and they're both the same base. So the only way this equation is true is if the exponents are equal to each other. And honestly, I don't want to work with the fraction, so I'm just going to multiply both sides by 2. So I've got negative 5x plus 12 equals 18x minus 38. X is to one side, so I've got 23x equals 38 plus 12, which is going to be 50. So x is going to be 50 23rds. There you have it. Okay, so one example. A little bit lengthy, though, okay. But you get the idea. Using lots of laws of exponents. All right, let's do another. Let's do 27 to the x squared equals 9. Okay, again, I want to write both in terms of the same base. That's going to have to be 3. So 3 cubed to the x squared equals 3 squared. Or 3 to the 3x squared equals 3 squared. Set the exponents equal to each other. X squared is 2/3. That means x is plus or minus, don't forget the plus or minus, the square root of 2/3. Or rationalizing that up, I got plus or minus is the same as square root of 2 over square root of 3. And let's just multiply the top and bottom by square root of 3. So x is plus or minus root 6 over 3. So those are your solutions to the second one. All right, so let's change it up a little bit, but not too much. Instead of having a base that's a number, let's do base e, which is also a number. I shouldn't say that. Let's, an obvious number, let's do, or an integer, I should say, let's do it in terms of the irrational number e, which remember is about 2.7. So let's see what we can do here. So getting used to the fact that e is indeed a number, not like I first said, not a number, it is a number. Okay, so 1 over e squared to the 4th. Okay. Clearly, the common base is going to be e. So let's write everything in terms of e. So I've got e to the 1/2 to the x. E to the x minus 7 equals 1 over e squared is just e to the negative 2. Power to power I multiply, so e to the 1/2 x times e to the x minus 7 equals e to the negative 8. Same base on the left, I'm going to add exponents, so e to the 1 plus 1/2 is going to be 3. Whoa, what was that? To the 3/2 x minus 7 equals e to the negative 8. Set the exponents equal to each other. So 3/2 x equals negative 1. So x is going to be negative 2/3. Okay, hopefully you're getting the hang of those types of problems. Writing both sides in terms of the same base, so using the laws of exponents. What about something like, let's do 2 of these types of problems. Something like 4, where I am actually not solving for the exponent. It's good to keep in mind that comparing this to other types of problems that involve exponents. All right, what about something like that? Solving for x. First thing, of course, is to isolate this x to the 2/3. And remember, my idea for the best way to solve these is to break up this exponent on the left. I would rewrite this as x to the 1/3 squared equals 9. And the reason I do that is the first thing I'm going to do is to get at what's x to the 1/3 by doing the square root of both sides. And remember, when you're solving for something squared, by taking the square root of both sides, you've got to put plus or minus. So x to the 1/3 equals plus or minus 3. And now I can raise both sides to the 3rd power to solve for x. So x equals plus or minus 3 to the 3rd, which is 27. Okay, let's do another one like that. And then we will talk about different types of problems here, so involving exponents. All right, so how about solving for 3x to the 3/4 minus 1 equals 23? All right, again, let's isolate the piece that has x. So x to the 3/4 equals 8. Again, follow what I did before. X to the 1/4 to the 3rd equals 8. Cube root of both sides. There is not plus or minus. So x to the 1/4, the cube root of 8 is 2. If it were -8, you'd put -2, but we'd have a problem with that in this case because you can't have something to the 4th root being a negative. So luckily it's just +8 here. So this is saying the 4th root of x equals 2. Raise both sides to the 4th power. X is 2 to the 4th, or 16. Okay, let's try something a little bit different here. Still involving, of course, exponents. How about let 3 to the x equal 5. Find 9 to the 2x minus 1. Okay, we did some of these problems in the worksheet, and again, we need to solve for 9 to the 2x minus 5, and I want to get it such that I can plug in for 3 to the x 5. So this is a matter of using the laws of exponents to undo this base to a power. Well, how did I get at 9 to the 2x minus 1? Well, I got that I could say this is same as 9 to the x times 9 to the -1. Or you could have said it's the same as 9 to the 2x over 9 to the 1. Either way, same idea. So that's where we're, because here, to go, the next step in this part would just be bring the next step in this part would just be bring the 9 to the -1 to the denominator. Okay, so we're looking at this here. Well, I still can't plug in 3 to the x, but I do know that 9 is 3 squared, so I've got 3 squared to the 2x over 9. And a power to a power I multiply, so I've got 3 to the 4x over 9. Now, how can I isolate so I have 3 to the x? Remember, a power, as we just showed, you multiply. Well, let's undo that. That's the same as 3 to the x to the 4th over 9. And now I can plug in what 3 to the x is. It's 5. So 5 to the 4th over 9, or 625 over 9. So it's undoing those laws of exponents, or using those laws of exponents to kind of undo this 9 to the 2x minus 1 so that I can plug in 3 to the x, plug in 5 for 3 to the x. Okay. All right, let's go, let's now talk about, I'm gonna go to the page here. Let's talk about exponential functions in general. A basic exponential function is y equals b to the x. And remember, to be exponential, b has to be greater than 0, and it cannot be 1. And the domain of a basic exponential function, say we were thinking f of x equals 2 to the x, there's no restriction on what I can put in for x in this particular case. However, the range for huge values, like of x, it's going to go towards infinity. But negative values of x, think of like 2 over -2 to the -10,000. That's the same as 1 over 2 to the 10,000. So the bigger the negative, the more it's getting closer and closer to 0. And there happens to be a horizontal asymptote at y equals 0. Okay, so let's do a graph here of an exponential function. Not going to be as basic as this, but what about if I asked you to graph? So graph f of x equals 3 to the x plus 2 minus 2. And I asked you to plot, at least 3 points. Well, first thing, it's a basic exponential, but it's been shifted down 2. So my new horizontal asymptote, in this case, is going to be y equals -2. And this will be confirmed when I start plotting some points. So pick some helpful points here. If I plug in, for example, 0, in order to find the y-intercept, I'm going to get 3 squared minus 2, or 9 minus 2, which is 7. So I've got 0, 7 as one of my points. Well, what about if I plugged in something like -1? If I plug in -1, I get 3 to the 1 minus 2, which is going to be 1. So -1, I'm going to be at 1. If I plug in -2, I get 3 to the 0, which is 1, minus 2, which is -1. So the graph is looking, whoa, imagine it's looking like that. And if you wanted to think about it in terms of transformations and comparing it to a parent graph like 3 to the x, it's been shifted to the left 2 and down 2. The domain of this particular function would be everything, and the range would be -2 to infinity. Oh, not negative infinity. So -2 to infinity exclusive. All right, speaking of domain and range, let's do a couple of those, everybody's favorite. Okay, let me add a new sheet here. All right, so I'm going to give you a variety of problems here. Let's start with, maybe I'll start with more basic. Well, I think it's more basic, but something I want to point out here, remember the base has to be greater than 0 and not 1. So the base of this exponential is not -2. If it was, there would be parentheses around the -2, which would make it, and we just said exponential, the base has to be greater than 0 and not 1. So this is the same. If it helps you, rewrite this as -1 times 2 to the x minus 5 minus 9. Okay, so let's start with generally what's easier, domain. Is there any restriction on what I can put into x in that exponent? Nope, there's not. Okay, now for the range. So again, if I can put in x minus 5, if I just think about what that exponent is, well, that's a line, and the range of the line is all reals. So when I do my range analysis, I'm going to have -1 times 2 to the negative infinity to infinity. Again, the range of x minus 5 is anything. Okay, so -1 times, well, 2 to the negative infinity is really close to 0. 2 to the infinity is huge. I'm going to multiply that by -1, that interval, and subtract 9. So it's negative infinity to 0 minus 9, or negative infinity to -9 exclusive. That's my range. Okay, let's step it up a little bit. Let's do f of x equals 2 square root of x plus 1 minus 7. All right, let's do the domain first. X can't be anything now because I have a square root. So I need, remember with the square root, if I'm domain and range is over the reals, I need x plus 1 to be greater than or equal to 0. So x has to be greater than or equal to -1. That's my domain. Now for the range, let's look at what we have here. X plus 1 is a line, and normally a line has a range of all real numbers. But because it's in a square root, the smallest it can be is 0. So I've got 2, the square root of 0 to infinity minus 7, or 2, 0 to infinity minus 7. Well, 2 to the 0 is 1. 2 to infinity is infinity. So I've got 1 to infinity, but then I've got to subtract 7. So -6 to infinity. That's my range. All right, let's do one more, which is the most difficult. Okay, let's call it g of x here, equals -3 square root of x squared plus 4 plus 2. And again, if it's helpful to you, write -1 times 3 square root x squared plus 4 plus 2. Okay, let's deal with the, actually, do I want to, I'm thinking about this for a second. You know what, I'm going to change it to make it a little bit more interesting. Let's make it x squared minus 4. X squared plus 4 is less interesting. Okay, all right, so let's start with the domain. X squared plus 4, not plus, minus 4 has to be greater than or equal to 0. Well, how do we solve an inequality that's not linear? I'm going to do sign analysis. This is a difference of squares. I need it to be greater than or equal to 0. So it's going to be positive in this case at the extremes. So the domain here is -infinity to -2, inclusive of -2, union 2 to infinity, inclusive of 2. Okay, so that's the domain. Now when I think about my range, let's go back to what we've got here. We've got a parabola. And when I look at this parabola without the square root, the range of this parabola would be this y-coordinate of the vertex, which is -4 to infinity. But because I'm under a square root, the smallest isn't going to be -4. I can't take the square root of a negative. The smallest is going to be 0. So I'm going to have -3, the square root of 0 to infinity, plus 2. So -3 square root of 0 is 0. And again, I think it might be helpful to you to rewrite this as -1 times 3 to the 0 is 1. 3 to infinity is infinity. But then you're multiplying by that -1, so -infinity to -1, and then adding 2. So -infinity to 1 ends up being your range there. So using the good tools we have from the past, like knowing the range of a quadratic, and then applying it under the square root, and then of course to the exponential function is important. And in terms of applications, yes, we did talk about interest compounded a finite number of times and compounded continuously, which are interesting problems, but they're going to be more interesting when we introduce logs when logs factor in. So I'm going to hold off on doing a video on that until after we incorporate logarithms as well. Okay, hope that helps.